Hi, Paul here from Easy Composites, and in this video I'm going to be showing you a really accessible method of making wing elements like these for motorsport. Downforce wings are a critical aspect of most aerodynamic packages in racing, and often during development you will have to iterate many different designs and develop and test them, and this can be a very time-consuming process. But in this video I'm going to be showing you a very fast and simple method to make a wing like this without needing any moulds. Instead, we'll be using Mylar to vacuum bag carbon fibre over a shaped foam core. Now, this method is not the type of construction that you would see in the top tiers of motorsport such as Formula 1 or in mass-produced wings. In both cases, these will be made using conventional moulds. But for the majority of club racers, Formula student teams, hill climbers, time attackers and so on, the speed and simplicity of this process would make it a highly suitable option. And if there is enough interest in this video, maybe we will go on to show how moulded wings are made in the future. In this video, I will be covering how to profile the foam cores using a Hotwire cutter, how to create suitable hard points and inserts, how to laminate and vacuum bag the carbon fibre onto the core using Mylar, and how to produce lightweight end plates using a Nomex honeycomb. In this video, I will be using CNC machinery. I'll be using a CNC router and even a CNC Hotwire cutter that I've built. But if you don't have access to equipment like this, please don't see it as an obstacle. Every step in this process can be easily done by hand, and I'll try and cover that as we go along. The first stage in the project is to cut the foam cores that we're later going to wrap the carbon fibre over. The type of foam that we're using for this is XPS, or extruded polystyrene. Now this differs from the conventional or more commonly found EPS, or expanded polystyrene, in that it has a really consistent finish. It doesn't have those beads that you typically find in packaging foam or common insulation. The reason that this is an advantage is when it's cut, it gives us a really flat surface finish. And that's important because it will translate into the final result that we get. Another advantage is its mechanical properties. It is much stiffer and stronger than typical EPS. And that's important because in the final product, this is going to be acting as a structural core. There are a few ways that you could go about shaping your foam. Probably the most basic would be to cut it using hand tools and sand it into your final profile. But that is likely to be very time consuming, particularly if you're looking to achieve a decent level of accuracy. If you are looking for a good level of accuracy, the fastest way to do this is going to be to use a Hotwire cutter. And a simple hand-operated bow cutter over some reference profiles is going to give you some really precise cores. If you're interested in learning more about this, there's lots and lots of information out there on Hotwire cutting, as it's a technique that's been used for many years by aero modelers to produce wings. For this project, I'm actually going to be using a CNC operated Hotwire cutter that I made for another project, and it's going to make really light work of this. This particular CNC can be operated in 4-axis mode to allow for tapered cuts, but for parallel cuts like these, you would only need 2-axis capability. Although there are commercially available Hotwire cutters, building one is actually very straightforward. As the machine does not get loaded during operation, light-duty components can be used. If you're interested in building your own, a quick search will bring up lots of information. Whether you are cutting by hand with profiles or using a CNC, it's very important not to cut too quickly. When cutting, the foam should be melting in front of the wire, meaning that the wire barely touches the material. If you cut too quickly, the wire will drag, which will cause it to arc and you will lose accuracy. For some perspective, I'm currently cutting at 200mm per minute. Now that we've got our cores made, we can go on and make the inserts. Because this wing is going to be mounted through its end plates, we're going to need some hard points in these locations, which will allow us to bolt it together securely. For that, I'm going to machine out some 8mm aluminium plate. I'm using my CNC machine for this, but of course it would be very straightforward to do this just using conventional machine tools. And if you were going for a very simple build, you could probably make these same inserts from plywood. This wing is only mounted through the end plates, so we only need inserts in those locations. But if you were centrally mounting it, then you would need to make some more for those locations. The cores and inserts can now be pre-assembled. So I'm just going to key back and degrease the aluminium components and then bond the assembly together using an ET500 epoxy adhesive. Now, because these bond lines won't be excessively stressed, you could use almost any adhesive for this as long as it doesn't attack polystyrene. Here, I'm filling and smoothing the gap between the two sections with adhesive. It's important to have a good transition here, as otherwise it could print through and be visible on the final part. One of the key aspects to this process is the use of Mylar to provide the moulded glossy outside surface. Now, Mylar is a type of polyester film which has some fairly unique properties that make it ideal for processes like this. It has a really good high gloss surface finish that resins don't stick to. Even without the use of release agent, it will easily peel off. And at the 125 micron that we stock, it has the perfect balance of flexibility and surface flatness for this sort of process. The Mylar is marked and cut to the exact width of the wing. As you will see later, accuracy is important here, as an overlap or undersize would be problematic to the process. In the other dimension, the film can be sized so that it wraps around the profile and protrudes on the trailing edge by around about 50 millimeters. To press the Mylar and carbon fibre firmly onto the wing profile, we'll be using a vacuum bag, which should be prepared in advance. So here I'm making up some envelope bags using the VB160 and applying the sealant tape, leaving just one side open and fitting the through bag connector. The next thing to prepare is the carbon fibre. For the visual surface ply, I'm using our 88 gram spread toe carbon. This will provide a really flat surface with very little print, which is ideal for aero parts, and also, let's be honest, it just looks great. Spread toe cloths are very delicate when cut and can fall apart quite easily. To avoid this, masking tape can be applied prior to cutting, which binds them together. These plies are sized to be around about 20mm oversize in both length and width. Following the 80 gram spread toe, I have also prepared 3 plies of 210 gram 2-2 twill for the main reinforcement. Due to the looseness of the spread toe weave, I have found that this particular moulding process can cause quite a lot of distortion to the weave pattern. But to stop this from happening, I've found that spray tacking the spread toe to the first backing ply does a great job of stabilising it. This is done with Fusion Fix and then rollered to consolidate, and then carefully rolled up with a paper separator ready for use. Right then, we have our cores assembled, we've got our Mylar and carbon cut to size, and our vacuum bag is ready to go. So we can now get on with the layup itself. The resin that we're going to be using for that is our EL2 epoxy laminating resin. Now, we will be mixing more resin than you would typically expect for a standard hand layup. Typically, you're aiming for around a 50-50 resin to fibre fraction, but for this project, it's actually going to be advantageous to have an excess of resin, and we're later going to be able to squeegee that out. So where you'd normally be aiming for a 50-50, we're actually going to go for 2 parts resin to 1 part fibre by weight. So we can weigh out the fibre, whatever we have there, we're going to double it and mix the same amount of resin. As always, the resin is accurately weighed out and thoroughly mixed for several minutes. Once mixed, about 1/3 of the resin can be poured and spread evenly over the Mylar, then the carbon fibre carefully laid down onto this. The resin can then be driven up into the fibre using a finned roller. Working the resin up through the laminate like this, rather than trying to wet out the fibre from the back, helps to reduce the amount of air that's entrapped and will produce higher quality parts. Once fully rollered, more resin can be spread onto the surface. This can then be rollered again and the whole process repeated until all the plies have been laid. Rollers are a good option for flat surfaces like this, but spreaders or squeegees can be used to a similar effect. Try to ensure throughout the layup that the resin is evenly distributed, and after the final ply you should be left with a fairly wet surface with a glossy film of resin. This is the excess resin that will help to allow the core to slide into position. The core can then be placed into position and the Mylar wrapped over. Adjustments should be made to align and position the core. At this stage, it is normal for the layup to seem quite loose on the core. After a quick wipe down, the assembly can then be placed into its vacuum bag. It should be positioned in the bag so that the leading edge of the wing is tight up against the fold in the bag, and any creases should be pulled and smooth flat. Then a strip of heavyweight breather is placed just behind the trailing edge, and the bag can be sealed and vacuum drawn. The vacuum drawdown should be done progressively. At each step of the drawdown, the Mylar can be squeegeed towards the trailing edge to tighten it onto the core and remove any air and excess resin. A simple but effective tool for this is a piece of foam with some breather wrapped over it. Once you're happy that the excess resin and air have been squeegeed out and the Mylar is sitting flat, the wing can be left to cure. It should be supported in such a way that the trailing edge flows straight from the profile. The secondary element is made using the exact same method as the primary. One thing that is worth mentioning about this layup and construction is that it has been optimised for simplicity over out-and-out performance. There are, of course, many ways to improve the layup of these elements. The most obvious being to include spars, which would transfer the load between the skins more effectively, meaning that the skins could be thinner, which in turn would reduce the weight. Simple spars can be made by slicing the core vertically and bonding in some pre-made carbon sheet. Of course, you could add further complexity by including spar caps and even ribs. The fibre type and orientation in this wing could also be improved. A simple 090 layup of a woven cloth will not yield the strength and stiffness that could be achieved with more careful placement. While experimenting with these more optimised constructions can be a lot of fun, they will add to the project's complexity and completion time, and it's really up to you if you deem them to be worth the effort. While the wing's curing, we can now get on and make our end plates. Now these are structural elements. They're going to be carrying all of the load from the wing down and into the chassis, so they will need to be very strong and stiff. Now the best way to make a stiff material is to create a sandwich structure. So we're going to be sandwiching carbon fibre either side of this 5mm Nomex. The carbon that we're going to be using is a 1mm spread toe material from our stock range of sheet materials that we manufacture. The blue colour that you see here, this isn't the final finish, this is just a protective film that I'll remove at the end. To cut these out, I'm going to load them onto a CNC and profile them. In these shots, it does look like there's a rough bird edge on the cut. This is only the protective film and the carbon itself is cutting underneath very cleanly. The cutter that I'm using is a 1.6mm carbide burr. Now this is the same kind of cutter that you would typically use for cutting out PCB material, and it does a great job at cutting carbon. In this particular example, I'm not using extraction, just so you can see the cutting happening, but normally you would be running this with full extraction. So we've got the plates off the machine and you can see that we've managed to achieve a really neat, accurate finish. Now if you did want to learn more about CNC machining carbon, we do have a video covering this subject where we go over how to do your tool pathing, how to optimise your feeds and speeds and really get the most out of machining this material. We also have a video that covers hand shaping and cutting methods. And actually carbon fibre is really easy to shape by hand, and so you certainly don't need CNC facilities to be able to carry out a project like this. If you are interested in seeing these videos, you can find them in the learning area on the Easy Composites website. The next thing that we need to consider are inserts within the core. Wherever we have fasteners running through these end plates, the bolts will put very high compressive load and that could crush the Nomex core in the middle. So to prevent this from happening, what we need to do is replace the core in these locations with a material that won't compress. Typically that's going to be aluminium, but it could be something as simple as plywood. And you would just put these inserts in wherever you're going to be drilling through for fasteners. Now in this particular project, I'm going to go one step further and pre-machine them. And this allows me to put in counterbores and adjustment slots. So these are all the inserts ready to go. All I need to do now is key these up with some 120 grit paper, degrease them and bond them into position on one side of the end plate. The adhesive I'm going to use for this is the VM100. The reverse side of these sheets is finished with a peel ply finish, so we don't need to do any further prep in order to get a good bond with the adhesive. When bonding aluminium directly to carbon fibre, you should decide whether galvanic corrosion is likely to be a problem in your application. As this is a wing on a dry stored race car, I'm not taking any measures as the wing will not be in the presence of any electrolytes that would facilitate the corrosion. But if your application does, maybe in a marine or conventional automotive application, then you should electrically isolate the carbon from the aluminium. The easiest way to do this is to laminate a thin layer of glass fibre between them. We'll set these to one side now for around 20 minutes to let the adhesive get to a good hold strength. We're now ready to cut our Nomex honeycomb. Now this is quite straightforward, just using a sharp scalpel. When I'm sizing this, I'm going to make it slightly smaller than the panel, and that way I'll be left with a gap around the edge that I can later fill to seal it. The cells on the Nomex do compress sideways very easily, and this helps to get a really close fit against the inserts, and slight distortion like this does not compromise the compressive performance of the core at all. We're now ready to bond this assembly together. The adhesive that I'm going to use for this will actually be made using the ER1 rapid repair resin. I'm choosing this resin because it has excellent adhesive and flexural properties, and it also cures very quickly for a resin system. But in order to make it appropriate for this application and change the viscosity, I'm going to first add some fumed silica. The fumed silica is added to the resin and mixed until the desired viscosity is achieved. Do bear in mind that the hardener will dilute it some, but you're aiming for a final viscosity that is about the same as a typical gel coat. Prior to adding the hardener, it should look a bit like this. This adhesive can then be spread evenly over the end plates at around 500 grams per square metre. A notch spreader can be useful for this, but on these small parts I find a brush works just fine. By slightly sliding the honeycomb once in position, you will force the adhesive onto the side walls of the cells, and this will help to form a fillet joint with a large surface area. The same sliding method can be used once the top plate is in position. We're now ready to vacuum press these together, and you'll see that I've already got the sealant tape set up and ready to go. Now if I was to just place a bag straight on top of this, I could run into a slight problem. Because of the overhang that I have of the skin past the core, it would force the edge of the skin down and potentially lift the inboard section up, meaning that I wouldn't get a proper bond. So to fix that problem, I'm going to use a spreader plate made of MDF. Vacuum bonding panels like this does not require full vacuum. In fact, using full vacuum can cause problems. The additional pressure would squeeze out all of the adhesive out from the edge of the cells, and also the additional movement of air during evacuation and potential for foaming the adhesive mean that regulating the vacuum to around 20% of full is preferable. I've repeated the exact same process on the second panel, so I can now leave these to cure under vacuum for around 6 hours. With the panels all bonded, all that's left to do now is fill this exposed edge using some of the VM100 adhesive. Once the VM100 is cured, it can be sanded in flat and taken to around 800 grit to provide a nice clean finish. We can now remove the cured wing elements from the vacuum bags. You can see here just how easily the Mylar releases from the epoxy, even without any form of release agent. Now we have the wing elements released, we can get this excess material trimmed off, we can clean up the ends, tap the holes and assemble the entire wing together. So here it is, our completed wing. As you'd expect, being carbon fibre, it's incredibly stiff, strong and lightweight, tipping the scales at only 3.5 kilos and able to withstand all of the downforce that it can generate. Now, if you are wondering just how much downforce this wing can take, look out for another video where we're going to test one of these elements right through to destruction. Looking at the end plates, we've got production quality finish here. We've got incredibly flat surfaces, and the VM100 has done an excellent job of capping the edge of that honeycomb panel. On the main wing elements, the Mylar has left us with a really good gloss finish over all of the surfaces. Now, of course, there are some compromises to this process. The main one being the flatness of the surface that we're able to achieve. Without having a perfectly flat mould to laminate against, getting a small degree of ripple on these surfaces is almost unavoidable. Now, it is more noticeable on these concave faces, but honestly, it is only very slight and it's not likely to have any real bearing on the performance of the wing. A wing made like this is also going to be slightly heavier than its moulded counterpart would be. That's owing to the higher resin ratio that we're going to get in the laminate. But all in, I still think this is an excellent solution for producing high-performance one-off wings. Remember that Easy Composites carries all of the equipment and materials required to complete a project like this, from the carbon fibre reinforcement and epoxy resin right through to the extruded polystyrene, Nomex honeycomb, vacuum equipment and consumables. As always, a huge thank you to all of our customers and subscribers for your support. If you do have any questions, I'd be happy to answer them below, and I'll see you in the next one. Of course, all of the equipment and materials that you've seen used in this video can be ordered online from the Easy Composites website. If you're based in the EU, you can now order directly from our Netherlands warehouse on easycomposites.eu, and for the UK and the rest of the world, please visit easycomposites.co.uk.